Welcome to Physics 101X Mechanics. This is an online version of Physics 101 at Rice University. We meet here in Hertzstein Amphitheater, where thousands of students have learned introductory physics, and also where they filmed the classroom scenes for The Evening Star, which was the sequel to Terms of Endearment. I believe Juliette Lewis sat right here. I would show you the footage to prove it, but we can't afford the copyright, and I don't think they bothered to digitize the film. The most important thing you can do to prepare for this course is to read the syllabus. The answer to almost any question you have is probably in the syllabus somewhere, so you will read the syllabus. Let's look at how the course is organized. It's broken into learning sequences, so maybe we'll be able to start with learning sequence 1. A learning sequence is about 1.5 weeks of material if this were an on-campus course. Of course, this is a student-paced course, so you can take as long or as short as you like. That material is broken into units, so maybe we'll be on unit 3, usually about 2 to 10 units, depending on how the material breaks up. And then there'll be boards, what we call boards. Maybe you'll be on board 2, and these are 5 to 10 minute lectures. I try to keep it closer to 5, but sometimes I can't. So you will watch and enjoy those lectures, and as you go across the top of the lectures, there will also be lecture problems. So that might look like LSX, some number, unit Y, some number, and then Pn, some number. So each unit will have a few lecture problems. These are really just conceptual problems. They're usually multiple choice, and you get infinite attempts to answer them. So hopefully you'll get a perfect score on lecture problems. At the end of the learning sequence, there'll be a homework. So this will be maybe 10 to 15 questions. They won't just be multiple choice, they'll also be numerical response and formula response. You'll get about 5 chances to enter the correct answer. And really, it's homework where you really learn the material, doing homework. And we like people to do homework together. So feel free to talk to people about it. Feel free to post a question in the discussion forum about how to get started or about some specific point. We just don't want anybody giving away explicit answers in the discussion forum. So the code for those, you'll be in some learning sequence X, and then homework N, or N might be 1 to 10, or 10 to 15. At the end, there'll be an exam. So the exam will look very similar to the homeworks. It will have, I don't know, probably more questions, about 20 questions. And again, multiple choice, numerical response, formula response. And the only difference is you can't get any help. So the exams are open book. You can use all the course material, but you can't ask for people for help in the discussion forum or anywhere else. You got to do the exam all by yourself. So the discussion forum I keep mentioning is a very useful way to interact with your fellow students. You can just go to it at the top and just start asking random questions, but you'll also notice we have a link below each one of these where people can just talk about that topic. So it's very useful if you use those links. For example, if you have a question about a homework, if you click the little forum link below, you can see where people also had a question about that same problem rather than searching in the main forum. So it's a pretty useful way to see what confused other people. It can also make you feel better and get the answer. Of course, there'll be no discussion of the exam on the discussion forum. In physics, we deal with very large and very small numbers, and we don't want to write them all down, so that's why we use scientific notation. So it is big and small numbers by powers of 10. So let's start by thinking about a typical number. How about my IQ? Here we go. My IQ, it's about 237. So what if we wanted to write that more easily? Well, in scientific notation, you always put the decimal here. So you'd say it's equal to 2.37. And then if we move the decimal 2 over, we must have to multiply by 100. We write 100 as 10 squared, 10 to the 2. So you're just counting decimal positions here with what's on your 10. Of course, that didn't really help us much, did it? We want to keep 3 digits. So we have 3 digits here, we have 3 digits here. It actually made it longer, having to write times 10 to the 2. We could have rounded it to 2 digits, right? These are the famous significant digits. How many are you going to keep, right? In this class, we're not really going to obsess with significant digits and significant figures like you might see in a normal physics class. The answers that you give in the homework problems are given a tolerance of 5%. So any answer you give, the grader is assigned to, if you get it within plus or minus 5%, you get it right. So keeping 3 significant figures should be perfectly adequate. But we're not going to get into the philosophy and rules of why we keep significant figures in this class. Let's look at a number where it might actually help us a little bit. Let's look at my EQ. Let's see, the last time I had it checked, my EQ was 624,987. So if I wanted to write that in terms of scientific notation, and I want to keep 3 significant figures, I always put the decimal here, 6.2, and then I round up to 4 because this is a 9. 6.25 times 10 to the 1, 2, 3, 4, 5, 10 to the 5. Okay? You know what EQ stands for, right? What does it stand for?
Emotional quotient.
Oh, I'm sorry. I thought it stood for something else. This is not my EQ. So my EQ, then, if that's what we're talking about, is 0.005379. Yeah, that one. Now we have a number that's really small, much less than 1, but we still do the same thing. It's 5.3, and I'm going to round it to 8, because I like 3 significant figures, and I move the decimal 1, 2, 3, 4, times 10 to the minus 4, because it's a small number. So now we have my EQ, my IQ. Let's think about how to combine them. Let's calculate the quality of a physics professor. That is basically equal to their IQ over their EQ. Maybe in the class you've taken before, you've been through something like that. So if we were going to do that, another advantage of scientific notation is you don't have to keep up with all the decimal points so well. You just have to say IQ over EQ, it's 2.37 over 5.38. You just write that down and you get 0.440. And then you take care of the decimals. You just have to add the decimals if you understand how powers work. So it's 2, and then it's minus because it's in the denominator, and then it's minus 4. Right? So it's 0.44 times 10 to the 6, or if you want to do it proper and move this over, it's 4.4 times 10 to the plus 5. So that's just a quick glimpse at how scientific notation works. I want to make sure you're well versed in it, and you probably already are if you've made it this far in life. But I will show you one thing that I can usually write on the board when I teach this class on the first day. I'll usually write this. 0.1 equals 1 times 10 to the minus 1 equals 0.1 times 10 to the 0 equals 10 times 10 to the minus 2 equals 10 to the minus 1. That is accurate. Everything there is true. And usually, with a few hundred brilliant Rice undergraduates here, at least one of them will raise their hand and say, no, wait, something's wrong. And they'll think one of them's wrong. But if you go through and you really understand your scientific notation, these are all the same thing. In this class, you're going to report a lot of numbers when you do a calculation. And of course, you've got to have these. You've got to have dimensions and units. It's basically what a number reports. If you give a number without a dimension or a unit, it's pretty useless. You'll find in this platform, whenever we have a homework problem or anything where you have to enter a numerical answer, the last part is always, what is the so-and-so in meters per second, in kilograms, in microjoules? We're always giving you the unit that we want, so be sure you answer numerically in the unit that we want. There's only 3 fundamental units in mechanics. There is the length in meters, and that's with an M, abbreviated with an M. There is time in seconds, and that's abbreviated with an S. And there is mass in kilograms, and that's abbreviated with a kg. Each one of these, it's fascinating how they came up with the unit and where it comes from and how the standard is defined. This to me is the most interesting though, is why did they put a prefix on the fundamental unit? Why is it kilograms and not grams? It actually has to do with the French Revolution and Napoleon, believe it or not, and Lavoisier. You want to be good at converting between different units, different combined units. So in addition to these 3, we can combine them to make meters per second for velocity or kilogram meters per second squared for force, etc. So you want to be good at jumping around. For instance, if I drove here at, say, 50 miles per hour, that's 50 miles per hour, sort of the manual way to convert it is to say, well, I'm just going to keep multiplying it by 1, right? So I got to get from miles all the way to meters if we ask you for the answer in meters per second. So let's say 1 mile is 5,280 feet, all right? I'm really just multiplying by 1 here because those two are equal, but then it cancels the miles, and then I have feet per hour, and then I'd say, well, 1 foot is 12 inches, and I'd say, okay, well, 1 inch is 25.4 millimeters, fine, and then I'd say 1,000 millimeters is 1 meter. Okay, we made it to meters. Oh, we got to do hours. Let's see, 1 hour is 3,600 seconds. And then, if you took the number, your answer, 50, whatever it is, and multiplied it by 5,280 times 12 times 25.4, divided by 1,000, divided by 3,600, then you'd have it. So you want to be good at converting units because you'll have to convert them a lot. It won't usually be something this strange, miles per hour to meters per second. So if you're dealing with a very large or a very small value with its unit, you could, of course, use scientific notation, what we just talked about. But sometimes we use a prefix instead of scientific notation. And you've seen these before. If something is times 10, that's deca, right? And the abbreviation for that is DA. That one doesn't come up too often, but a decameter would be 10 meters. Times 100 is hecta, and that one is HA, I believe, no, just H. So a hectometer is 100 meters. But then something that comes up more often is times 10 to the 3. Times 1,000 is kilo, which is K times the unit. So 1,000 meters is a kilometer, kilometer. 1,000 seconds is a kilosecond. And look at that, they use kilo in the fundamental unit for mass. Again, French Revolution, look it up. These numbers go on to ridiculous limits. 10 to the 6 you might see is mega, right, big M. 10 to the 9, then we know them from computer terminology. 10 to the 9, of course, is giga, big G. It goes on and on. 10 to the 12 is tera, 10 to the 15 is peta, 10 to the 18 is exa. Then they turn into sort of like Marx Brothers. 10 to the 21st is zeta, 10 to the 24th is yada. And there's actually a move afoot to make 10 to the 27th hella. I don't know if it's going to happen or not. It's going to be big H, a hellameter. You can also go the other direction. So you can have 10 to the minus 1, and that's deci. That doesn't come up too much. Little d. Let's get to the important ones. Times 10 to the minus 2 is centi. Right, a centimeter, of course, is a little c. And then the big one, 10 to the minus 3 is milli. And I always want to put 2 L's in it, but that's my problem, is a little m. Right? Others you might see in this class, we might see micro and nano. Right? So 10 to the minus 6 is micro. Oh, and it's a mu. So you got to practice writing your mu's. Oh, no, you don't, because you're on a computer, whatever. And then 10 to the minus 9 is nano, the most important one here at Rice, and that's a little n. So you want to be familiar with these. Occasionally we might ask for an answer in a non-standard prefix, like micronewtons. So be ready. I often get asked this question: why is physics so hard? I actually get asked it like this: why is physics so hard? Sometimes. So here's why. I think I figured out why. Is because you can't do anything without math. Right? Physics is entirely mathematical. We have almost 0 lists of things to memorize, and people will tend to be better at memorizing lists than doing math. Really, all of mechanics is like 3 concepts, and the rest is mathematical manipulations of those 3 concepts. So generally what you find is the further along you are in math, the better you do in physics. That's just kind of how it is. Now this course, and a lot of physics courses you take, will be calculus-based. I often think that's kind of a silly thing to say because all of physics is calculus-based. You can't really do physics that isn't calculus-based. But what we mean by that is we show you the calculus. We use calculus to solve certain problems. And we show you that all those formulas you're usually memorizing are really special cases where we apply calculus to get formulas that you like to memorize. Really, you can do everything with calculus. That doesn't mean you have to be an expert in calculus to succeed in a course like this. Usually people think, well, the more calculus you have, the better you're going to do. Not necessarily, because usually in a physics course like this, when we come to some integral, right, we're doing calculus with an integral, people initially panic. But often in physics, we explain how you set up an integral and why you need the integral. And sometimes that actually helps you learn it better than you do in your calculus class. A lot of people say, actually, integrals made a lot more sense when I saw it in physics. It's not because we explain it better, it's just because we have it tied to the real world, and you already saw it once before in your calculus class. But I actually don't think it is knowledge of calculus that necessarily defines how successful you'll be in the class. I think it is more efficiency with algebra. If you're good at calculus, or if you know a lot of calculus, you've had a lot of experience with algebra. So what I've found holds up students sometimes is, say we have a formula like this, d equals 1/2 at squared. And we say, let's solve this for t. Well, in a physics class, we're going to say, oh, well, then t is the square root of 2d over a. Right? We've done a lot of algebra in our lives, and we kind of know, okay, I bring the 2 over here, it's 2d, I divide by a, 2d over a, I take the square root. And we just go straight to that step. We don't actually write out and think about, okay, I'm going to multiply both sides by 2. I mean, this is a fine thing to do when you're getting started. Right? But I actually find it's really, if you're really used to algebra, thinking about algebra. So just keep that in mind as you're going. If you're struggling, think, maybe I just need to think about the algebra more, practice algebra a little bit more. So I raised the question of why would we put a prefix in our standard unit in the MKS system for mechanics. If you really want to know, I'm going to tell you right now. If you don't really care, move on. This isn't really that important. And I want to make it clear, I am not an historian by any sense of the word, okay? But I do have Wikipedia, and I have the internet, and I can read about things. So this is something I read 4 or 5 years ago that I'm pretty sure is true, and this is my memory of it, with apologies to real historians. So a lot of the standardization of measurements was happening in the 18th century in France. For commerce, you know, we need everybody to be weighing the same amount. We need everybody to have the same amount of mass, and everybody to have the same amount of length and the same amount of time. So Lavoisier was a chemist working on these standardizations, and sort of the winning standard at the time for mass was the grave, meaning heavy, weighty, important grave. Problem was, Lavoisier also was a little bit of a tax collector, and in the whole revolution that wasn't really popular. So he ended up getting executed. And the revolutionary government said, no, we don't want to call it the grave. That sounds too important. We're going to go with this new standard, the gram, which means small and common and more like what they wanted. So they're running along with the gram, and they figured out it's too little. It's not big enough. We need a heavier standard of mass. So of course, what happened is we ended up with the kilogram, 1,000 grams, which is pretty much was the original grave. Because Lavoisier, you know, he was a pretty smart guy.